I'll start with a sort of grand vision, and then gradually during the talk we'll go kind of back to down to earth. So don't get perturbed too much if this sounds very, very ambitious, let's say. So I'll start with the general motivations for this research program. So take it as a description of a research program that is unfolding, and that I'm very pleased to be able to present here, because in a way, as Vlatko was saying, this is a natural continuation of the sort of revolution that happened with quantum information that was fueled by lots of discoveries that happened here at CQT as well. And what I'm going to talk about is a possible way forward to use some of the tools that have been developed in quantum information to imagine what could be done beyond something like the universal quantum computer. And so I'll start with 3 reasons why one might want to do that, because of course we all like quantum information, and it sounds like a very complete theory. It sounds like it's giving us lots of good technological developments as well. So one might wonder, why would we ever want to do something different from that, or new? So the first point is that so quantum information theory, all the theorems that we prove in this context, assume all of quantum theory's properties. And quantum theory is, as we know, is a very powerful general theory, but it's also highly specific. So in a way, it's got a lot of both formal and conceptual machinery that we borrow in quantum information and we use to prove all the major results in this discipline. But if you look at physics at large, you will see that actually quantum theory may not be the last thing. Actually, in fact, there could be a better theory coming along which will unify quantum phenomena with gravitation, for example. And so we might want to be prepared to leave some of the aspects of quantum theory behind, while still retaining the idea that quantum information processing is possible. And so to talk about this, one both needs conceptual tools and formal tools beyond the ones that we developed so far. So I think this is one of the first motivations I want to provide for this kind of program. And of course, there's a second motivation, which is that despite the name, a universal computer is not the most universal machine you can think of. So universal computer, following a definition that Deutsch gave, elaborating on that Turing proposed, is a programmable computer whose repertoire contains all computations that are physically allowed. So it's the union of all physically possible repertoires. But there are some tasks that don't fall into the model of computational tasks. So there are some tasks that a universal computer is not able to perform. And I think this was already clear to vonNeumann, who wrote a beautiful essay, a number of beautiful essays, but in particular one of them I have in mind, where he points very clearly out the fact that, for example, a universal computer wouldn't be able to self-reproduce. Of course, imagine you're given a universal quantum computer, and then you want to program it so that it will be able to create an exact replica of itself. And there is no such program, because the universal quantum computer is not such a machine. It can operate on its workspace, on its register, but it's not designed to take some raw materials and build a new copy of itself, which is something, on the other hand, that, let's say, living cells do all the time. So there are tasks that are not in the universal computer's repertoire. And the other thing, of course, is that universal computers must be built out of something. And whether or not they can be built is actually a question that is decided by the laws of physics as a whole, and not just by the principles of quantum information theory. Quantum information theory is a very, very special application of quantum theory where we are assuming we've got unlimited resources like blank qubits that we can use in order to perform computations. But from cosmology, we know that in reality that might not be the case. And so whether or not a universal computer can be built in the first place depends on resources available and on the particular interactions that are made available to us from fundamental physics. And so out of these considerations came this idea that vonNeumann had to generalize the universal computer to an even more powerful machine, which is a universal constructor. And a universal constructor, informally speaking, is an object which has in its repertoire all physically possible transformations, not just computations. So it will in particular be able to build a universal computer if that's allowed by the laws of physics, and it will be able to build a replica of itself too. And this is quite cool, and it's also cool because it kind of gets close to what we know is a special property that living systems have. And I think that's why vonNeumann was so interested in it. And not just him, actually Turing too. So, second reason why somehow we might want to step out of quantum information theory by itself. The third reason is that quantum information theory has put together, in fact, two ways of formulating laws of physics that we have in fundamental physics. One is dynamics. Of course, we use a unitary transformation to compute the effect of certain gates on certain input states. But the other mode of explanation in physics is the mode that uses physical principles. And if you think about it, it's a very, very different mode from the dynamical law kind of approach. Okay? And I put here three examples that I find interesting of this other mode of formulating laws of physics. So there's the conservation of energy, which rules out a perpetual motion machine. It's very funny when you browse the internet for these perpetual motion machines, incidentally, you find all sorts of very inventive proposals that unfortunately don't work. But this one was by a guy called Boyle, who was trying to use some principles of the way in which water flows in small capillaries to try to create perpetual motion. And of course, it doesn't work because actually water can creep up like this only if this is lower than the level of this water fluid here. But so if you have a kind of moment to go on the internet and browse for these things too, because it's really fun. So conservation of energy rules this out. But to know that this is impossible, you don't have to compute specific consequences of dynamical laws. The principle is just formulated like that. A perpetual motion machine of the first kind is impossible. There are no dynamical laws, no initial conditions. You could then prove that a certain dynamical law is compatible with this principle, but the principle is more general. It somehow transcends dynamics. So, in a sense, it's more powerful. And quantum information is full of these principles, is full of these kind of statements, such as things about channel capacity and statements about what one can do with entangled states and, let's say, local operations on subsystems of an entangled pair and so on. The second principle, of course, is the second law of thermodynamics, which rules out a different kind of perpetual motion machine, which converts completely heat into work. And unfortunately, we also know that's not possible. Again, on the internet, you go and you see this very nice image where there's a boat, which is sort of propelled forward from kind of drawing up heat from the water and converting the whole of that into mechanical work with no waste. And unfortunately, that doesn't work, again. And then we have a maybe more positive principle here, which there's a question mark there because we don't know whether that's true. It's the principle that says that a universal computer is possible. And there's a kind of question mark there because it doesn't stand in the same class as the other two principles because, let's say, it's more like a conjecture. And what is there is an interesting cartoon which represents one of the first computers, mechanical computers that were proposed by this guy called Babbage and by Ada Lovelace, who together tried to realize this machine, which was called the analytical engine. And if you look into the nice notes, you will see that actually this is one of the first ideas for a programmable universal machine. And this came well before Turing. It's just that, unfortunately, they couldn't realize it. So they ran out of funds. You know, I feel kind of good because, you know, it's not just us struggling with funding, but, you know, this was already a problem in the Victorian era. I think actually Ada went into gambling. Well, you know, she was going to horse races to try to raise funds for this thing. It didn't work. And I'm just saying, I mean, I would. So I know there's always some kind of last resource I can resort to if I'm really desperate as far as funding is concerned, but never mind. So this is just a curiosity, but it's a fun fact. So these three are examples of principles. And so we can maybe imagine a generalized lesson from these three principles. The question is it possible to use this principle-based way of explaining things and providing laws, etc., to have predictions, to make predictions about physical systems just as well as we do given dynamical laws, such as Newton laws, the laws of gravitation, and the laws of quantum theory. But with a gain, which is that we don't have to commit to a specific dynamics, but we can make these more general statements and try to apply these principles even in cases like when you're considering a gravitational system which interacts with a quantum system, where we don't have necessarily a dynamical law ready and known. And so I will try to convince you that it is possible, and also I will try to say that solving this problem somehow is also helpful to address the other two important problems that we mentioned in the first two slides. So all of these things go hand in hand, and constructor theory is supposed to provide a way of using this logic. Yes?
Is there any other approach if you don't have a specific proposal for dynamics beyond quantum theory? What could you hope to do other than use kind of broader physics?
Yes, that's a great question. By the way, if you want to interrupt for questions, I welcome them, so please do. So one way is to use approximation schemes. So of course we've been doing this for a long while in physics. So things like open system dynamics is one example in quantum theory where you might decide to neglect part of your environment because you might not be able to model it fully, but then you can make some assumptions about a general behavior of this environment, such as, you know, you can imagine weak coupling, you can imagine various approximations that you can make in order to solve a certain dynamical problem for a smaller system, let's say. So that's one way you can go about, so making approximations. But somehow it seems to me that if you choose that road, you will still have to make a certain number of very stringent assumptions about the dynamics, and maybe you will lose the generality that you have here. So the hope in a way is to combine these other ways of going about when you don't know exactly what the dynamics is with this more general approach to make progress. Okay? Okay, so here is an example. This is not constructor theory, but it's an example of what the logic should be when you decide to leave dynamics behind. So Bondi is a physicist who was a physicist interested in field theory and general relativity and astrophysics. He proposed this very interesting argument to argue for this phenomenon that is called redshift, which is actually a consequence of general relativity, but without actually using the laws of general relativity at all. That's kind of cool. And I want to kind of walk with you through the steps of this argument to see how it works. So the assumptions are energy conservation, which is a principle, and then you have the equivalence of mass and energy, which allows you to say somewhat that if you have an atom which is on the some sort of ground state like that, you can assign some mass to it, and if it's in this excited state, you can assign a different mass which is larger than this little m here. And now you can try to imagine what would happen if you didn't have redshift of photons in a gravitational field, whereby the frequency of a photon which is climbing up this field should change. Imagine you don't have that, and you still hold tied to these two principles, you will end up with a contradiction. So you in particular will violate the conservation of energy. Therefore, there must be something like redshift. That's the kind of logic that we're following here. So you're imagining a seesaw, which is made, I mean, this is very challenging, of course, it can't be done experimentally, but it's in principle, it's a thought experiment. There's a pivot here, this is a seesaw-like thing. There's a gravitational field out there. And you start in this configuration when the excited atom, which is heavier, is here, and the de-excited atom is there. And then you trigger, with producing some work, you can use some laser or something, you trigger some emission from this excited atom, which therefore goes into the non-excited state. And here you have a photon and two mirrors that are perfectly reflective. Now, this photon will hit the mirror here, and imagining a very, very efficient process, the photon will climb up, gravitational field is here, and at this point will be reflected by this other perfectly reflecting mirror and absorbed. So this guy will have now a higher energy, therefore a higher mass. And at this point you can see that because of the gravitational field here, this seesaw will be such that this M here goes down and this one goes up, so you end up in this configuration. And you can extract mechanical work at this step. You can put some spring here, some flywheel, which will get mgd worth of mechanical work. And now you can apply an adiabatic swap, so you just go back to this original configuration by rotating the two masses, or the two atoms, however you want to consider them, and you're back to the original state. So you've got a cycle. And interestingly, you spent W0, which is a constant fixed amount, and you have gained mgd. And by making d as large as you like, you will be able to extract as much work as you like from this. And clearly this is a contradiction of the conservation of energy, so it can't be. Therefore, something must have gone wrong in these steps. And what went wrong is that I didn't consider that the photon climbing in the gravitational field changes its frequency. And therefore, it won't be absorbed with the same efficiency, 1, which I assume there. So this scheme won't work deterministically because there is redshift. Okay? So this is just a digression to say in what way this kind of logic is useful and can lead us to make predictions that are more general than, yes?
Isn't the whole point that in many situations in physics you have an equivalence between, I mean, principles and dynamical laws are sometimes two ways to look at the same phenomenon. Like you have the principle of least action, classical mechanics, and you have the dynamical law, and you get the same result. And so it's not surprising that using this logic, you come to the same conclusion, right?
Well, the principle of least action is a specific principle that you assume within a certain dynamical framework, whereas conservation of energy in this form is much more general in the sense that you can define it within any theory that allows the concept of energy.
But the two assumptions are basically the ones that Einstein used to derive the laws of general relativity, right?
Well, not just those two. There's also the equivalence. There are a number of other assumptions, right? And also, of course, the laws of GR are much more precise because they allow you to say exactly by how much the photon frequency has to change, which this, of course, doesn't tell you that. But suppose you didn't know about the laws and you ran this argument, this would be a guideline for, let's say, conjecturing the laws. So on the one hand, you can say that the principles, if you prefer to think of them like that, they are like a general guideline for approaching the problem of conjecturing new laws, okay? Okay, so now I'll outline briefly what the general ideas of constructor theory are as they were originally conceived, and now I'll go into 3 applications of this logic, which are something I've been working on. So the problem of constructor theory is to, instead of using dynamics as your primitive element, to formulate laws as scale-independent principles about what tasks are possible, what tasks are impossible, and why. And so the dynamics is not assumed, but it should be a consequence of these principles. And some of these principles will be new principles different from those that we already know. So that's important to bear in mind. So this is like the program as David Deutsch conceived of it a while ago. And the question is, of course, you might be by now be very skeptical about all of this, because you will say, okay, drop dynamical laws, where do I start? Well, if you drop dynamical laws, you still have a concept of state, and you still have a concept of transformation. So you can at least say what a task is. So I said the laws have to be formulated as statements about possible and impossible tasks or physical transformations. So tasks are formalized in this way, and lots of people working here on resource theory and maybe also category theory will see a number of nice formal connections with this stuff. And the core difference from the idea of a dynamical trajectory comes here, because we say that a task, physical transformation, is impossible if there is a law of physics that forbids its being performed to arbitrarily high accuracy, and it's possible otherwise. So think of the difference between possible task, as defined here, and allowed transformation in a dynamical law. In a dynamical law, any trajectory which is a solution of the dynamical equations is an allowed trajectory. Here, a possible task is not just that. It's a transformation which can be performed to arbitrarily high accuracy on a system when it's coupled to any kind of environment. So if you think of, let's say, what happens when you imagine a NOT gate being performed in a computational network, the fact that we think that the NOT gate is possible means that we know that the laws of physics allow for an ever-improving sequence of gates that approximately perform NOT, but the reason why we think it's possible is that we don't have any law that says that there is a finite value of accuracy beyond which we can't go. So when you say that something is impossible, conversely, you are stating that there is this limit, that there is this fundamental limitation. So for example, in the case of the conservation of energy, that implies that there is a fundamental limitation beyond which you can't go as far as perpetual motion machines are concerned. They will always be very faulty. No cloning is another example. If you try to create a cloning machine that clones two non-orthogonal states, you will see that there is a fundamental limit in accuracy beyond which you can't go. And in that case, we say that the task is impossible. Otherwise, the task is possible. And if the task is possible, you can model what that means, imagining a dynamical law. So to have a model in terms of dynamics of what possible means, you can think of it as meaning that for a possible task, there exists a system which is a constructor, which has the property that when coupled to the system in question can perform the transformation and stays unchanged in the ability of causing the transformation again. So it can act like a cycle. So again, those who work on resource theory, this will be very reminiscent of the concept of a catalyst. Okay? But in this case, it's supposed to be more general. And so that's all as far as general constructor theory is concerned. Now I will give you 3 examples of where this logic is useful. So this is a general program, and there are 3 cases where this approach was useful to show something of interest. So the first application is the one that I was mentioning. So imagine you have a system which I call a hybrid system. Again, the word has been used in the past to mean other things, but I'll give you here the definition under which I'm working. So a hybrid system is one where there is some mystery system, that's why there's an M there, a system about which we know very little, may not obey quantum theory. which is coupled to a quantum system. So this could be, for all practical purposes, a qubit. And you're trying to make some predictions about the composite system. You can assume that these two can couple, at least in some basis, let's say, but you're not sure whether M really obeys quantum theory or not. And you, therefore, are not sure whether you can, for instance, apply some approach like master equations or open system dynamics kind of logic. So we want to do something more general here. Why is this interesting? Well, this is interesting because there are a number of cases where we are actually looking at a system like this in current contemporary physics. One is the case where M is the gravitational field and Q is some mass which is behaving like a qubit and is superposed across two different locations. And this is a problem that bothered Feynman already. I think Vlatko and others have already talked about this topic a number of times here in CQT. The problem here is we have this system where a quantum object interacts with gravity, and we would like to make some statements about whether gravity obeys quantum theory too and behaves in such a way that, for example, it gets entangled with this qubit, just like the photon field would. Or it's a completely classical field, or in fact it behaves in more exotic ways, which we don't yet know. And I think this is a general problem that quantum gravity people are worried about. So that's one example. Another example that comes to mind is when you're thinking of a quantum system interacting with some object that may well obey overall quantum theory, but may be undergoing some decoherence, let's say. And so M could be a living system, biological system, for instance, that you want to show as some coherent behavior together with Q. So this is a kind of different scenario where we know the laws that the system obeys, but yet we can't assume that they hold overall for Q and M together, okay? So in this case, in constructor theory, you can formulate a general theory of information which allows you to make some assumptions about M that eventually lead to making predictions about the composite system QM together. And this has nice implications for gravity. And so I'll go through some of the definitions that one proposes in this constructor theory of information. So the important key thing is the concept of an information medium. So an information medium is a generalization of a familiar classical bit. So it's a system with a set of attributes which can be all permuted. So if you think of a bit, there are two states, 0 and 1, and can be all permuted. So 0 can go to 0, and 1, and likewise for 1, 1 can be sent to itself and to 0. And another task is also possible in this set of attributes of the information medium. It's the task of copying the states in the set X. So an information medium is a system that has at least one such set. And of course, you can think of a quantum system with one of the orthogonal bases will qualify as an information medium. We know we can use it for classical information processing. Note the fact that we state this by using the concept of possible and not using dynamical laws. Now, you can then formulate a principle about this media, which is called the interoperability principle. And this is a bit like, it imposes some kind of nice group theoretic property on these sets, in the sense that it says that if you take any two information media and you put them together, the combined object is still an information medium. So thinking of an example, if you consider a qubit which is kind of embodied in a photon, and you imagine it interacting with a solid state system qubit, we never bothered to think whether it's possible to consider the combined entity of the two qubits as being a system which can, as a whole, encode at least 4 bits of information. We just assume that to be the case. But it's a very remarkable property of physical systems. And this principle just exposes what it is about the physical systems that we are assuming in that case, which will be very important to make predictions in the case that I mentioned earlier, where you have a quantum system and another system that you don't know exactly how it works. So under this framework, you can show that quantum systems are in fact a special case of information media. And you can define a class of objects called superinformation media that generalize quantum systems in the sense that they have all the qualitative properties of a quantum system, but they don't necessarily obey quantum theory. They only obey these general constraints about possible and impossible transformations. And so armed with this setting, you can then go back to the problem that we were considering earlier and try to prove something about the situation where you have this quantum system interacting with something that you don't know exactly what to assume of. So to do that, we need to, with this framework, we need to define what non-classical means. And non-classical in the following will mean that a system has at least two information variables, x and z, that are not copyable simultaneously to the same actors. Of course, here you see a lot of properties that are implicit in quantum theory, but we're trying not to assume that. And then we can assume two more general principles, locality, which is a well-known principle, and this interoperability of information that I mentioned earlier. And then we can go back to this problem that I was considering earlier, to a slight variant of it, where we have a system made of this mystery system M, of which we're trying to establish at least if it's classical or non-classical. And then we have two quantum systems that probe it. And so we can prove this nice theorem that says that if these two quantum systems start in a state which is not entangled, and then they end up being entangled through interaction with M, and M is assumed to be at least an information medium, so it's assumed to have at least one classical basis where you can encode information, then actually M must be non-classical. So this is an example where by using these general principles you can end up making an interesting predictions about M by saying that if it can entangle two other quantum systems, then it has to be at least non-classical in the sense that I said earlier. It may not be fully quantum, we don't know, but it's a nice prediction because you can then go back to this problem of gravity and say, well, what if I were able to entangle two quantum masses just through gravitational interaction? This is something that Sugato Bose in London and Vlatko and I and Sugato's team have been thinking about quite a lot over the past years. The question is, what if you could entangle actually two masses, each one of which is a qubit, through this mediator M, and M being gravity? Using this general theorem, you can conclude that the mediator, gravity, has at least to have these non-classical features that we mentioned. So it may not be a full quantum system, but it cannot be completely classical in the way that, let's say, Einstein's theory of general relativity or quantum field theory in curved spacetime would suggest. So this is an interesting application, okay? And of course, this is just illustration that some people in Oxford produced with qubits, where they were trying to illustrate the principle behind this entanglement formation, where the mediator here, the mystery system, is simulated by these two qubits, and these other external qubits are the two quantum systems that you're trying to entangle. And of course, when these are qubits, it's obvious why the intermediate system has to have coherence in order for these two qubits to get entangled. But the point of the simulation is to show that you can make this conclusion even when you don't assume that these two intermediate qubits are actually qubits. In fact, in the case of gravity, if it can be used to entangle two other quantum systems, it must be itself, let's say, very close to a qubit, so it has to be non-classical. Okay, so that was the first application. And of course, here there are some more applications of this logic that I mentioned earlier. That you can try to use the same logic to show that, let's say, a bacterium or let's say a bacterium that is sensitive to light and couples to the light field has to have some non-classical feature in it when it's capable of entangling, let's say, two photons or two subsystems of the field of light. So that's one application. And there are more, a number of other designs of experiments and simulations that you can imagine along the lines of trying to simulate these systems that obey these general constructor theoretic principles, but not quantum theory as a whole. So let's go for the second application. So the second application is on a different, along a different line, and this is to do with the problem of irreversibility. So it's well known that, so earlier when I mentioned the principles, I talked about the second law of thermodynamics. It's actually a principle that is quite different from the others that I mentioned. So it's different from the conservation of energy because unlike the conservation of energy, the second law of thermodynamics is a scale-dependent principle. So it's formulated usually to a certain level of coarse-graining. It relies on a number of statistical approximations or procedures. So it's only valid in a certain domain of applicability, which is, let's say, called the macroscopic domain. So the idea is that irreversibility under time-reversed symmetric laws is usually emergent once you make a certain number of assumptions. And these assumptions are those that statistical mechanics is concerned with. Now, using the idea of a constructor, maybe there is an additional source of irreversibility that we can see in a system even under time-reversed symmetric laws, and this is what I would like to mention here. So there is a different way of formulating the second law, which was known to the founding fathers of thermodynamics, so Kelvin, Clausius, and Planck specifically, which is stated in a very constructor theoretic way, if you like, because it says it's possible to construct a device which can which can increase the temperature of a fluid by mechanical means only. So you can imagine here, this is a stirrer, there's a weight, and the temperature increases once the weight goes down. Imagining this container to be sealed, adiabatically isolated. But if you try to create a similar machine that only by mechanical means cools the water down, that is impossible. What you need is a heat sink. You need another kind of side effect in addition to the mechanical means like side effect. So it's very interesting that this is not just about the impossibility or the possibility of a certain trajectory, but it's about the possibility or impossibility of a machine that does a certain transformation according to, so only having a certain mechanical side effect. And now we can try to imagine a toy model that expresses this kind of irreversibility. And this is based on a general idea of irreversibility, which says that a certain task, x goes to y, let's say, is possible, but its transpose is not. So read here, a constructor is allowed for this task, but it's not allowed for the transpose task when you invert the input and the output. And this is a different kind of irreversibility from the standard one that's considered in thermodynamics and in statistical mechanics in general. So it's more similar to this phenomenological thermodynamics, which currently has been slightly neglected, I would say, in favor of the statistical mechanics approach. And it's interesting. Now, the toy model I want to consider uses a very interesting quantum information tool, which was devised by some people here and their collaborators, which is called the homogenization machine. This is a very simple tool to describe what happens when a system equilibrates with a larger bath or system, which is at a certain temperature. But it does so in a very nice unitary and quantum theory compliant way. So just follow me as I'm explaining this. So the homogenization machine scheme, which is a model that I use to prove the point about reversibility, is a system made of n qubits. So you see them here. You imagine this as being an array that goes round here with periodic boundary conditions in a way. So 1, 2, 3, and then n minus 1, n. And they're all prepared in the same state. And you can couple it with an external qubit through a unitary transformation, which is a partial swap operation, which leaves the qubit alone with a certain probability cos eta squared, and it swaps it with the qubit in the reservoir with 1 minus that probability. And what is proven in these nice works is that this is a universal machine to perform a task of sending a qubit from any state rho to any state psi. This is just another way of saying that if you have a very large system and you put another system close to it in a different state, it will rapidly equilibrate and assume the same state as approximately as the systems inside the reservoir, with an accuracy which increases as the number of systems in the reservoir increases. Now, therefore, it looks like that this is an equally good machine for any such task. So if you take any two states, rho goes to psi, for instance, a pure state goes to a maximally mixed state. This scheme will just work as well when you're trying to do pure to mixed, compared to the case where you have mixed to pure, which is the reverse task. Now, what happens though is that if you try to consider how well this machine performs as a constructor, in other words, how resilient it is, how many times you can reuse it after you use it once. So if you want to now bring a second qubit and use the same machine to perform the same task, so therefore you're looking at whether this is a good constructor for the task in question, there is an interesting irreversibility that pops up. And so if you consider this special case of a task which has a pure state going to a maximally mixed state, it turns out that this quantum homogenizer does very well when you consider just one usage of the machine. But when you consider repeated usages, the case where you're trying to send a pure state to a maximally mixed state, which in a way is an easier task because maximally mixed states are, as we know, more robust than pure states. In that case, the homogenizer is very robust, and therefore it qualifies as a constructor, if you like. But if you consider the reverse task, it's no longer the case. And so there is a sense in which there is an irreversibility induced by the requirement of the system being a constructor. In one case, the system is a constructor. If you consider the transpose task, where you go from a maximally mixed state back to a pure state, the system is no longer a constructor. So this is an illustration of why this idea of possible and impossible might be an interesting, useful idea to solve some of these problems to do with incorporating behaviors that we think are not compatible with time reverse symmetric laws within the dynamical picture in a way that's exact. And it could be an alternative route to the statistical mechanics route. And there's a big question mark as to how the two relate to one another. It's that's object of some future work that I'm doing.
So here,
yes.
I understand that that's really just the correlations being wiped out at the end. If I think about what the reason why we can't do this in reverse is because to do this properly in reverse, one has to account for your qubit to be correlated with all of the...
Yes, but this is true just if you consider the task... Sorry. This would be true even just considering the task being performed once. If you discard the reservoir, or if you forget about the correlations between the qubit and the reservoir, I mean, you could do the unitary transformation backwards, of course. So there is, actually, in these two papers, this is a thing that's being pointed out, which is part of the reason why we expect thermalization to work, is because we are forgetting about correlations. But there is an additional irreversibility in the sense that has to do with the capacity of the constructor to be reused in one way, in one case or in the other. So let's put it this way, the performance of this machine for the forward task is somehow the same if you just consider one single shot event. But if you then consider how resilient the machine is by keeping the same scheme, and you consider the two tasks, one the forward task and the reverse task, you will see that the machine performs differently in one way or another as a constructor, so as a cycle. So in one case, you can actually approximate the behavior of a cycle well, in the case where you go from a pure to a maximum mixed state, whereas you can't the other way around.
Go to the second and third.
Yeah, so it's a bit like saying that there is an additional reason why you would expect irreversibility.
Remember all previous interactions to be able to reverse the population.
Yes, that's correct.
So you need a huge memory overhead as an agent if you wanted to see a reversal.
Yes, but then it would be a different machine. So let's say you don't need it in the forward direction, in the backward direction you do need it.
Yeah.
So that's actually a nice way of putting it.
So by performing differently in the backwards task, you mean it's not, you cannot really do it to any degree of accuracy, and so this is why it's not a
yes, that's right.
Not a possible task.
Yes, this is correct.
Okay.
Yes.
Because you could do it, but the efficiency is, the performance is so bad now in the other direction.
Yes, there's a subtlety that would come out if I could show. Maybe I can discuss it later with on the whiteboard. But so the subtlety is this. The asymmetry shows up only if you consider reusing the same machine with the second or third or nth qubit. Yeah. Which, so therefore, the efficiency for a single usage is the same in both directions. But it's a bit like, you have a fridge, you put a can of Coke inside and you want it to be refrigerated, and you want to use it again for a different can of, and so on. And the point is that in this case, for the forward direction, the fridge seems to keep up with the task fairly well for a number of usages. Whereas for the reverse task, there is a rapid deterioration, which no doubt is due to, of course, the kind of task I chose, because it's a pure to a mixed state, maximally mixed state, so it's a special case in a way. But it's not immediately explained through, oh, I neglected correlations. So it's an additional, let's say, source of irreversibility, and kind of we can debate how it relates to the other and whether it's the consequences of the other or not. But it's just to draw attention to this notion of a constructor, which adds to, let's say, the understanding of what's going on in this particular situation. So, third application, and I'm reaching the end. It's going to be very quick. It's a captive audience, right? So there is this statement like the audience is locked in and can't go. So you're not captive, so I'll try to kind of reach the conclusion fairly quickly. So this question has been considered a number of times. I think in a way it's a tried question, and some people in the audience will have thought about it carefully because they're interested in foundations from many different angles. Some other people are maybe a bit more dismissive of foundations as well, so they will have thought about the question from that angle too. Now, the point I want to make here is that, so you've got this point here, quantum theory, and this is an imaginary space. As I was drawing this slide, I thought it wouldn't make any sense, actually, because I noticed later that it might be a bit confusing, but never mind. Still makes the point, I hope. So, one way in which you could try to vary a theory is to vary its formalism, its formal aspects. So you can, let's say, plus, you can add a term in the dynamical equations, you can modify the parameters that appear in the in the equation in question, and you can do a number of other things. So let's say you can vary its formalism, but you can also vary, let's say, the principles it's supposed to obey. So for instance, you tobe is the conservation of energy. Let's try to see what happens if it suddenly no longer does, to the degree that we suppose the theory, to the degree that we expect the theory to obey the principle. Of course, conservation of energy is not a good idea, but there are other principles that quantum theory obeys, which could be varied, and which we could see what exactly in quantum theory would then have to be disposed or left behind. So, of course, the two things are not independent, because if you change the formalism, you might end up having a theory that no longer obeys, for instance, certain principles that quantum theory obeys, and likewise, if you modify some principles that quantum theory obeys, you might end up also changing its formalism. But the point I want to make is that I would like to now go into this direction, trying to modify some of the principles that the theory obeys, and this goes into that direction. So before you read these slides, just listen to what I'm saying. So the quantum theory has a number of axioms, and we all encounter them as we go through various courses on the topic. And amongst these axioms, there is this one called the Born rule, which is interesting because it adds on top of an otherwise deterministic theory an aspect which is probabilistic. So it says that the expected value of a certain observable is a certain function of the observable and the quantum state. Or if you like, it can be formulated in other ways too. But it adds a probabilistic element to a theory that otherwise is not probabilistic, because the Schrödinger equation or the Heisenberg equation of motion is just a deterministic law. And so in a way, it's an interesting axiom. And there have been lots of attempts to try and derive it from other axioms or principles. This way is using some of these information theoretic principles that I mentioned earlier to derive this Born rule-like behavior. And possibly the reason why this is interesting is that the principles that one can use in order to derive the Born rule-like pattern that we expect by just using some principles and quantum theory without the Born rule is that these principles are information theoretic in nature. So we go back to this reason why it's interesting to discuss it here, because the principles I'm talking about are, I won't discuss them here, I can discuss them later in the questions. They have this information theoretic basis. And so it would be interesting to see what happens if we vary those principles slightly. What would happen to the Born rule itself? So once you can show that you derive the Born rule from those principles, then you can modify them and then see what type of rule emerges out of these modifications. And I think this is a nice open question that I would like to consider in the future. And so, future directions. There is an interest from a number of people, including a PhD student I'm working with, to endow this theory with a deeper mathematical structure, so drawn from category theory, which is like a nice tool to describe these kind of structures with tasks. And hopefully this could clarify also the idea of possibility as rooted in this notion of a constructor. Of course, then quantifying the various degrees of non-classicality within the framework that I described earlier, without having to use all the tools that quantum theory gives us. And this might involve drawing a connection with current other approaches, such as GPTs. And you may have applications to understanding a bit better the information theoretic structures of current proposals for quantum gravity, such as loop quantum gravity. And then there is this interesting challenge which came out of this toy model that I presented, which is to understand how the second and the third law that I didn't mention of thermodynamics could be phrased with this emphasis on possible and impossible rather than on allowed trajectories, which is the focus of statistical mechanics. And then going into crazier and crazier directions, which is what sounds like a good ending point. Of course, ultimately, if this program works, it would be very nice to have it would be necessary to have a way of deriving the current dynamical laws from the principles. And then there is this problem, therefore, deriving dynamics out of these timeless principles. And note that this is a problem that has been, to some degree, addressed in quantum theory. There are some proposals. There's this nice page in Wood's proposal that was made at some point in the 80s, and a number of developments on that in various fields, including quantum gravity. But let's say constructor theory will have to deal with this problem, so that's one of the things that will have to be solved. And of course, there is this issue that I mentioned at the start of understanding under what conditions the generalization of a universal computer, which is this universal constructor, might be possible. And just the last point I want to mention is this fact that we have this interesting branch that was somewhat very important for the early days of quantum information, which is complexity theory. Complexity theory is somewhat concerned with computational tasks, but of course it would be nice to have a complexity theory of any kind of task. And so this complexity theory should be somewhat generalized to incorporate the idea of a universal constructor. So if the idea of a universal constructor works, then you would have to also to expand the field of complexity theory to cover a machine that can perform any physical transformation that's physically allowed. And so with these broad ideas, I'll conclude, and this is my quote for the day. So in science, one is always concerned with putting the best face on one's ignorance. The scientist's knowledge is always very limited, and one has to make the best with what one's got. And I hope I did that today. Thank you for listening.